Welcome to the Vector Academy, School of Physics. Let's look into problems in physics for IIT JEE on temperature and thermal expansion. Question 1. In a temperature scale X, ice point of water is assigned a value of 20 degree X and the boiling point of water is assigned a value of 220 degree X. In another scale Y, the ice point of water is assigned a value of -20 degree Y and the boiling point is given a value of 380 degree Y. At what temperature the numerical value of temperature on both the scales will be same? We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. We can consider temperature scales for X and Y as illustrated in figure. Here X lies in the range of 20 to 220. And Y lies in the range of -20 to 380. Total units in temperature scale X is 220–20. That is 200 units. Total units in temperature scale Y is 380––20. That is 400 units. Clearly, 1 unit of X equals 2 units of Y. At a particular temperature, if we are A divisions away from 20 degree X and B divisions away from -20 degree Y, then we have 20 plus A equals -20 plus B. 20 plus A equals -20 plus 2A. Or A equals 40. Question 2. The length of the mercury column in a mercury and glass thermometer is 5 cm at triple point of water. The length is 6.84 cm at the steam point. If length of the mercury column can be read with a precision of 0.01 cm, can this thermometer be used to distinguish between the ice point and the triple point of water? We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. The triple point of water is the temperature and pressure at which the three phases of water, that is solid, liquid and gaseous, coexist in thermodynamic equilibrium. The triple point of water is 0.01 degrees Celsius. The steam point of water is the temperature at which water vapor condenses at a pressure of 1 atmosphere. The steam point of water is 100 degrees Celsius. The ice point of water is the temperature at which fresh water freezes. The ice point of water is 0 degrees Celsius. The length of mercury column increases linearly with temperature. In the given question, it is 5 cm for triple point of water, that is 0.01 degrees Celsius. And it is 6.84 cm for steam point of water, that is 100 degrees Celsius. Change in temperature of 99.9 degrees Celsius from 0.01 degrees Celsius to 100 degrees Celsius causes a change in length equal to 1.84 cm. That is 6.84 cm minus 5 cm. Change in temperature of 0.01 degrees Celsius will cause a change in length equal to 1.84 divided by 99.99 multiplied by 0.01, which is equal to 0.00018 cm. Hence, the thermometer will fail to distinguish between the ice point and triple point, as precision of thermometer is only 0.01 cm. Question 3. What effect the following changes will make to the range, sensitivity and responsiveness of a mercury and glass thermometer? A. Increase in size of the bulb. B. Increase in diameter of the capillary bore. C. Increase in length of the stem. D. Use of thicker glass for the bulb. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Bulb of thermometer. The bulb in a thermometer is filled with mercury. When the bulb is heated, mercury in the bulb expands and rises up in the capillary tube. The height of the mercury gives the reading of temperature. Capillary tube in thermometer. The capillary tube of a mercury thermometer is the long cylindrical tube that is connected to the bulb. As temperature increases, mercury flows up the capillary. Length of stem in thermometer. Magnified glass makes up the outside jacket of the thermometer, which is called the stem. Sensitivity of thermometer. The sensitivity of a thermometer is defined as the increase in the length of the mercury column per unit increase in temperature. Responsiveness of thermometer. How small a change the unaided human eye can see a change against a scale. When size of the bulb is increased, its volume increases, resulting in decrease of height or range of mercury level. Sensitivity increases as more length is covered per unit increase in temperature due to short range of thermometer. Responsiveness or precision decreases due to short range. When diameter of the capillary tube is increased, its volume increases, resulting in range increases as more mercury can flow to greater heights. Sensitivity decreases as less length is covered per unit increase in temperature. There is no change in responsiveness. When the length of stem is increased, range increases. There is no change in sensitivity and responsiveness. When thickness of glass for bulb is increased, there is no change in range and sensitivity. Only responsiveness decreases. Question 4. The focal length of a spherical mirror is given by f equals r divided by 2, where r is radius of curvature of the mirror. For a given spherical mirror made of steel, the focal length is f equals 24.0 cm. Find its new focal length if temperature increases by 50 degrees Celsius. Given thermal expansion coefficient of steel equals 1.2 into 10 to the power of -5 per degree Celsius. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. With rise in temperature, radius of curvature of a spherical mirror increases, given by R final equals R initial multiplied by 1 plus thermal expansion coefficient into change in temperature. Rise in radius of curvature of a spherical mirror leads to rise in focal length of mirror. R initial equals 2 multiplied by focal length, which gives 48.0 centimeters. R final equals R initial multiplied by 1 plus thermal expansion coefficient into change in temperature equals 48.0 multiplied by 1 plus 1.2 into 10 to the power of -5 into 50. Therefore, new focal length equals 48.0288 divided by 2, which gives 24.0144 centimeter. Question 5. A pendulum-based clock keeps correct time in an aeroplane flying uniformly at a height h above the surface of the Earth. The cabin temperature inside the plane is 10 degrees Celsius. The same pendulum keeps correct time on the surface of the Earth when temperature is 30 degrees Celsius. Find the coefficient of linear expansions of the material of the pendulum. You can assume that h is much less than r radius of the Earth. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Time period of simple pendulum is 2 pi under root L upon g effective. You can go through the detailed derivation of this relation for time period of simple pendulum. Gravitational force at height h, that is g dash equals g multiplied by 1 minus 2h divided by r. You can go through the detailed derivation of this relation for gravitational force at height h. Time period t dash at height h and length L at 10 degrees Celsius is equal to 2 pi under root L upon g multiplied by 1 minus 2h divided by r. Time period t on the surface of the Earth and length L dash at 30 degrees Celsius is equal to 2 pi under root L multiplied by 1 plus coefficient of linear expansion into change in temperature divided by r radius of Earth. Since t dash equals t, we get coefficient of linear expansion alpha equals h divided by 10r. Question 6. A liquid having coefficient of volume expansion gamma is filled in a cylindrical glass vessel. Glass has a coefficient of linear expansion of alpha g. The liquid along with the container is heated to raise their temperature by delta T. Mass of the container is negligible. A. Find relationship between alpha g and gamma if it was found that the center of mass of the system did not move due to heating. B. Find relationship between alpha g and gamma if the fraction of volume of the container occupied by the liquid does not change due to heating. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. The center of mass will not move if the height of liquid column in the container does not change. Let original volume of liquid, area of cross-section of the container and height of liquid be V0, A0 and H0 respectively. Then we have H0 equals V0 divided by A0. If temperature increases by delta theta, then V equals V0 multiplied by 1 plus coefficient of volume expansion gamma into delta theta. And A equals A0 multiplied by 1 plus 2 into coefficient of linear expansion alpha into delta theta. Therefore, height of liquid after heating, H equals V divided by A, which gives H equals H0 multiplied by 1 plus coefficient of volume expansion gamma into delta theta divided by 1 plus 2 into coefficient of linear expansion alpha into delta theta. If H equals H0, then 1 plus gamma into delta theta equals 1 plus 2 alpha into delta theta. Coefficient of volume expansion gamma equals 2 into coefficient of linear expansion alpha. Let original volume of the liquid and the container be VL0 and VC0. At increased temperature, we can find VL and VC. VL equals VL0 multiplied by 1 plus coefficient of volume expansion gamma into delta theta. Vc equals Vc0 multiplied by 1 plus 3 into coefficient of linear expansion alpha into delta theta. We can then easily calculate the fraction VL divided by Vc. For fractions VL by Vc to be equal to VL0 by Vc0, we must have 1 plus gamma into delta theta equals 1 plus 3 alpha into delta theta, which finally gives coefficient of volume expansion gamma equals 3 into coefficient of linear expansion alpha. Question 7. A water in glass thermometer has density of water marked on its stem. Density of water is the thermometric property in this case. When this thermometer is dipped in liquid A, the density of water read is 0.99995 gram per centimeter cube. Thereafter it is dipped in liquid B and the reading remains unchanged. Maximum density of water is 1.0 gram per centimeter cube. A. Can we say that liquid A and B are necessarily in thermal equilibrium? B. If two liquids are mixed and the thermometer is inserted in the mixture, the height of water column in stem is found to change. That is, reading is different from 0.99995 gram per centimeter cube. Has the height increased or decreased? We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Here, water in glass thermometer means that water is filled inside capillary tube instead of mercury. Here, density of water is the unit of measurement of temperature instead of degrees Celsius measured due to expansion or contraction of mercury. The density of water changes with temperature as shown in the figure. From the curve, we can conclude that it is possible that the density of water is same at different temperatures. Increase in temperature leads to low density of water and hence high readings in water in glass thermometer as water becomes less dense and so it will rise high. Since it is possible that the two liquids be at different temperatures Q1 less than 4 degrees Celsius and Q2 greater than 4 degrees Celsius and still, the density of water can remain same. So we cannot say that liquid A and B are necessarily in thermal equilibrium. When liquids at Q1 and Q2 are mixed, the mixture will have a temperature between Q1 and Q2. It means density of water will increase and height of water column in the stem will decrease. Question 8. Two metal plates A and B made of same material are placed on a table as shown in the figure. If the plates are heated uniformly, will the gap indicated by X and Y in the figure increase or decrease? We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Since both A and B are made up of same material, their coefficient of linear expansion will be same. Let coefficient of linear expansion of both A and B be alpha. Change in length L1 due to increase in temperature is given by delta L1 equals L1 into coefficient of linear expansion alpha into change in temperature delta theta. Change in length L2 due to increase in temperature is given by delta L2 equals L2 into coefficient of linear expansion alpha into change in temperature delta theta. Since L1 is greater than L2, delta L1 will be greater than delta L2. Therefore, gap indicated by X will increase. It is easy to understand that when both A and B are heated uniformly, length of both A and B will increase and hence Y will contract, decrease. Question 9. Containers A and B contain a liquid up to same height. They are connected by a tube. See figure A. If the liquid in container A is heated, in which direction will the liquid flow through the tube? B. If the liquid in the container B is heated, in which direction will the liquid flow through the tube? Assume that the containers do not expand on heating. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. When liquid in container A is heated, its density ρ will decrease slightly as volume of the liquid will increase on heating. Its height will increase due to thermal expansion of liquid on heating. Here increase in height will be very less due to the V shape which will cover more area rather than height. Here, decrease in density ρ will be more significant than increase in height h. Hence, effective pressure, P equals ρgh will decrease. Liquid always flows from high pressure to low pressure. So, liquid flows from B to A. When liquid in container B is heated, its density ρ will decrease slightly as volume of the liquid will increase on heating. Its height will increase due to thermal expansion of liquid on heating. Here increase in height will be greater due to the reverse V shape which will cover less area and hence more height. Here, decrease in density ρ will be less significant than increase in height h. Hence, effective pressure, P equals ρgh will increase. Liquid always flows from high pressure to low pressure. So, liquid flows from B to A. Question 10. Height of mercury in a barometer is H0 equals 76.0 cm at a temperature of θ1 equals 20 degrees Celsius. If the actual atmospheric pressure does not change, but the temperature of the air, and hence the temperature of the mercury and the tube rises to θ2 equals 35 degrees Celsius. A. What will be the height of mercury column in the barometer now? B. If the scale for reading the height of mercury column is marked on the glass tube of the barometer, what reading will it show? Coefficient of volume expansion of mercury and coefficient of linear expansion of glass are gamma Hg equals 1.8 into 10 to the power of -4 per degree Celsius. Alpha G equals 0.09 into 10 to the power of -4 per degree Celsius. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Variation of density with temperature. With rise in temperature, density decreases. For first part of the question, we just have to calculate the increase in height of mercury column in the barometer regardless of readings on the glass tube of the barometer. It is given, P initial equals P final. Here, change in temperature equals 15 degrees Celsius. Let density of mercury at θ1 be ρ0. Then, initial pressure, which is atmospheric pressure P0, equals ρ0 into g into initial height h0. Now density of mercury at temperature θ2 is ρ equals ρ0 divided by 1 plus gamma hg into delta theta. Therefore, final pressure is given by P equals ρ0 into g into h divided by 1 plus gamma hg into delta theta. From 1 and 2, we can equate P initial equals P final, which gives new height of mercury column in the barometer, h equals 76.205 cm. For B part, actual height of Hg column at changed temperature is h equals h0 multiplied by 1 plus g into gamma hg into delta theta. But the glass scale also expands and the reading shown by it will be less than h given above. A reading of 1 cm on glass scale at θ2 actually represents a length equals 1 cm multiplied by 1 plus alpha g into delta theta. Therefore, a length h will be read by the scale as h divided by 1 plus alpha g into delta theta, which gives reading for the height of mercury column to be 76.195 cm. Question 11. Pendulum of a clock consists of very thin sticks of iron and an alloy. At room temperature, the iron sticks 1 and 2 have length L0 each. Length of each of the two alloy sticks 4 and 5 is small l0. And the length of iron stick 3 measured up to the center of the iron bob is lambda 0. Thickness of connecting strips are negligible and mass of everything except the bob is negligible. The pendulum oscillates about the horizontal axis shown in the figure. It is desired that the time period of the pendulum should not change even if temperature of the room changes. Find the coefficient of linear expansion alpha of the alloy if the coefficient of linear expansion for iron is alpha 0. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Time period of simple pendulum. Time period of simple pendulum is given by t equals 2 pi under root length L of pendulum divided by gravity g. Clearly, time period of simple pendulum depends on length L of pendulum. In order to keep the time period of simple pendulum constant, change in length L of pendulum should be 0. Here, length of pendulum L equals L0 plus lambda 0 minus small l0. And change in length of pendulum delta L equals delta L0 plus delta lambda 0 minus delta small l0. In order to keep the time period of simple pendulum constant, change in length delta L of pendulum should be 0. It gives 0 equals L0 into alpha 0 into delta theta plus lambda 0 into alpha 0 into delta theta minus small l0 into alpha into delta theta. Solving it gives alpha equals L0 plus lambda 0 into alpha 0 divided by small l0. Question 12. Two samples of a liquid have volumes 400 cc and 220 cc and their temperature are 10 degrees Celsius and 110 degrees Celsius respectively. Find the final temperature and volume of the mixture if the two samples are mixed. Assume no heat exchange with the surroundings. Coefficient of volume expansion of the liquid is gamma equals 10 to the power of -3 per degree Celsius. And its specific heat capacity is a constant for the entire range of temperature. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Variation of density with temperature. Final density ρ equals initial density ρ0 divided by 1 plus coefficient of volume expansion gamma into change in temperature delta theta. Specific heat capacity. The specific heat capacity of a material is the amount of energy required to raise 1 kg of the material by 1 degree Celsius. In the given problem, no heat exchange with the surrounding takes place. Hence, total energy of the system will remain constant. That is, final energy equals initial energy. Mass of sample at 10 degrees Celsius is m1 equals ρ10 into v10 equals ρ10 into 400. Mass of sample at 110 degrees Celsius is m2 equals ρ110 into v110 equals ρ110 into 220. Since density at temperature 110 degrees Celsius equals density at temperature 10 degrees Celsius divided by 1 plus gamma into change in temperature 100. We get m2 equals m1 divided by 2. When mixed, let the final temperature be theta. Since total energy of the system is constant and specific heat capacity S is constant, we can write m1 into S into theta minus 10 equals m2 into S into 110 minus theta. On solving, we get the final temperature after mixing two liquids to be theta equals 43.33 degrees Celsius. Mass of mixture equals m1 plus m1 divided by 3 equals 3m1 divided by 2. Volume of 3m1 by 2 mass of liquid at 10 degrees Celsius will be equals 3 by 2 times 400 equals 600 cc. At 130 by 3 degrees Celsius this volume will become V equals 600 into 1 plus 130 by 3 minus 10 into gamma, which gives the final volume after mixing to be 620 cc. Question 13. A composite bar has two segments of equal length L each. Both segments are made of same material, but cross-sectional area of segment OB is twice that of OA. The bar is kept on a smooth table with the joint at the origin of the coordinate system attached to the table. Temperature of the composite bar is uniformly raised by delta theta. Calculate the x-coordinate of the joint if coefficient of linear thermal expansion for the material is alpha per degree Celsius. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. The center of mass of an uniform rod is L divided by 2. Let mass of OA equals m. Then mass of OB equals 2m. The center of mass of segment OA equals center of mass of segment BO equals L divided by 2. When temperature of the composite bar is uniformly raised, change in length L' equals original length L into coefficient of linear thermal expansion alpha into change in temperature delta theta. Hence, the center of mass of segment OA equals center of mass of segment BO will become L' divided by 2. Or L alpha delta theta by 2. When temperature of the composite bar is uniformly raised, both segment OA and BO will expand. Since mass of segment OA is less than mass of segment BO, the center of mass of segment OA will move to left by x plus L alpha delta theta by 2. And the center of mass of segment BO will move to right by L alpha delta theta by 2 minus x. For center of mass of the composite rod to remain unmoved, we must have m into x plus L alpha delta theta by 2 equals 2m into L alpha delta theta by 2 minus x. Solving it will give the final value of x. Therefore, x-coordinate of joint is minus L alpha delta theta by 6. Question 14. Two rods of different metals having the same area of cross-section A are placed between the two massive walls as shown in figure. The first rod has a length L1, coefficient of linear expansion alpha-1 and Young's modulus Y1. The corresponding quantities for second rod are L2, alpha-2 and Y2. The temperature of both the rods is now raised uniformly by T degrees. A. Find the force with which the rods act on each other at higher temperature in terms of given quantities. B. Also find the length of the rods at higher temperature. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Young's modulus is the ratio of stress and strain. Here, stress is force per unit area, and strain is change in length per unit original length. When the temperature is raised by T, then increase in length of first rod equals L1 alpha 1 T. An increase in length of second rod equals L2 alpha 2 T. Therefore, total increase in length equals L1 alpha 1 T plus L2 alpha 2 T, which can be written as T into L1 alpha 1 plus L2 alpha 2. As the walls are rigid, the above increase will not be possible. This will be compensated by the force F producing decrease in the length of the rods. Decrease in length of first rod equals F into L1 divided by Y1 into A. decrease in length of second rod equals F into L2 divided by Y2 into A. Therefore, total decrease in length due to F equals F upon A into L1 by Y1 plus L2 by Y2. As the walls are rigid, total increase in length should be equals total decrease in length due to F. That is, F upon A into L1 by Y1 plus L2 by Y2 equals T into L1 alpha 1 plus L2 alpha 2. Or F equals AT into L1 alpha 1 plus L2 alpha 2 divided by L1 by Y1 plus L2 by Y2. Length of the first rod equals original length plus increase in length due to temperature minus decrease in length due to force F. That is equal to L1 plus L1 alpha 1 T minus FL1 upon AY1. Similarly, length of the second rod equals L2 plus L2 alpha 2 T minus FL2 upon AY2. The total length will remain unaltered. Question 15. Two rods of equal cross-sections, one of copper and the other of steel, are joined to form a composite rod of length 2.0 meters. At 30 degrees Celsius the length of the copper rod is 0.5 meters. When the temperature is raised to 130 degrees Celsius the length of the composite rod increases to 2.002 meters. If the composite rod is fixed between two rigid walls and is thus not allowed to expand, it is found that the lengths of the two component rods also do not change with the increase in temperature. Calculate the Young's modulus and the coefficient of linear expansion of steel. Given Young's modulus of copper equals 1.3 times 10 to the power of 11 Newton per meter square. Coefficient of linear expansion of copper equals 1.6 times 10 to the power of -5 per degree Celsius. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Here, length of the copper rod at 30 degrees Celsius is 0.5 meters. Hence, length of the steel rod at 30 degrees Celsius will be 2.0 minus 0.5 equals 1.5 meters. For copper rod, change in length, Lt minus L0, when the temperature is raised from 30 degrees Celsius to 130 degrees Celsius is given by coefficient of linear expansion of copper alpha Cu multiplied by L0 of copper multiplied by change in temperature. Putting values we get change in length for copper equals 50 into alpha Cu. Similarly, for steel rod, change in length, Lt minus L0, when the temperature is raised from 30 degrees Celsius to 130 degrees Celsius is given by coefficient of linear expansion of steel alpha S multiplied by L0 of steel multiplied by change in temperature. Putting values we get change in length for steel equals 150 into alpha S. Total change in length equals 50 alpha Cu plus 150 alpha S. Here, alpha Cu equals 1.6 into 10 to the power of -5 per degree Celsius. Solving for alpha S gives Coefficient of linear expansion of steel alpha S equals 0.8 into 10 to the power of -5 per degree Celsius. According to the given question, there is no change in length of individual rod. So the length change due to stress is balanced by the length change due to thermal expansion. Stress in steel rod equals Young's modulus of steel Ys into strain equals Ys into delta L upon L0 of steel equals Ys into alpha S into delta T. Similarly, stress in copper rod equals Ycu into alpha Cu into delta T. But stress in steel rod equals stress in copper rod. Therefore, Ys divided by Ycu equals alpha Cu upon alpha S. Or, Ys equals Ycu into alpha Cu upon alpha S. Putting the values we get Ys equals 2.6 times 10 to the power of 11 Newton per meter square. Question 16. A beaker contains a liquid of volume V0. A solid block of volume V floats in the liquid with 90% of its volume submerged in the liquid. The whole system is heated to raise its temperature by delta theta. It is observed that the height of liquid in the beaker does not change and the solid is now floating with its entire volume submerged. Calculate delta theta. It is given that coefficient of volume expansion of the solid and the glass beaker are gamma S and gamma G respectively. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Let ρL and ρS be the initial densities of the liquid and the solid respectively. Since solid is floating with 90% of its volume submerged inside liquid, the density of solid is less than the density of liquid. And the ratio of density of solid to density of liquid is 0.9. On increasing the temperature by delta theta, density of solid increases to become ρS multiplied by 1 plus coefficient of volume expansion of the solid gamma S into change in temperature delta theta. On increasing the temperature by delta theta, density of liquid increases to become ρL multiplied by 1 plus coefficient of volume expansion of the liquid gamma L into change in temperature delta theta. Since, on increasing the temperature, solid completely submerge in liquid, their density become equal. That is, ρS multiplied by 1 plus gamma S into delta theta equals ρL multiplied by 1 plus gamma L into delta theta. Or, 0.9 into 1 plus gamma S delta theta equals 1 plus gamma L delta theta. V0 equals original volume of liquid. V equals original volume of solid. Volume ABCD before heating equals V0 plus 0.9 V. Volume A-B-C-D- after heating equals V01 plus gamma L delta theta plus V1 plus gamma S delta theta. On increasing the temperature, volume of glass beaker increases to become V0 plus 0.9 V multiplied by 1 plus gamma G into delta theta. The liquid level will not change if volume ABCD of the container expands to be equal to volume A-B-C-D-. We 0 plus 0.9 we multiplied by 1 plus gamma g delta theta equals we 0 multiplied by 1 plus gamma l delta theta plus we into 1 plus gamma s into delta theta. Since 0.9 multiplied by 1 plus gamma s delta theta equals 1 plus gamma l delta theta. We 0 plus 0.9 we multiplied by 1 plus gamma g delta theta equals 0.9 we 0 into 1 plus gamma s delta theta plus we into 1 plus gamma s delta theta. We 0 plus 0.9 we multiplied by 1 plus gamma g delta theta equals 0.9 we 0 plus we into 1 plus gamma s delta theta. Solving it will give the final value of delta theta. Question 17. Assume that the coefficient of linear expansion of the material of a rod remains constant, equal to alpha per degree Celsius for a fairly large range of temperature. Length of the rod is L0 at temperature theta 0. A. Find the length of the rod at a high temperature theta. B. Approximate the answer obtained in A. To show that the length of the rod for small changes in temperature is given by L equals L0 multiplied by 1 plus alpha into theta minus theta 0. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Let the length of the rod be L at temperature theta. A small change in temperature by delta theta will cause the length to change by delta L equals alpha L delta theta. It implies integral of delta L upon L over L0 to L equals alpha into integral of delta theta over theta 0 to theta. Solving which gives L equals L0 multiplied by e to the power of alpha into theta minus theta 0. It is known that e to the power of x equals 1 plus x square by 2 factorial plus and so on. When x is small, e to the power of x is approximately equals 1 plus x. Since L equals L0 multiplied by e to the power of alpha into theta minus theta 0. Therefore, L is approximately equals L0 multiplied by 1 plus alpha into theta minus theta 0. Question 18. In a compensated pendulum, a triangular frame ABC is made using two different metals. AB of length L1 is made using a metal having coefficient of linear expansion alpha 1. BC and AC of length L2 each have coefficient of linear expansion alpha 2. A heavy bob is attached at C. Pendulum can oscillate about the pivot D. Find L2 divided by L1, so that distance of bob from the pivot point D does not change with change in temperature. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. In triangle ADC, we have DC square equals AC square minus AD square. Or we can write y square equals L2 square minus L1 square upon 4. Differentiating both sides we get 2y delta y equals 2L2 delta L2 minus 2 by 4 L1 delta L1. Since Distance of Bob from the pivot point D, that is y, should not change with change in temperature. Change in y, that is delta y equals 0. Putting delta y equals 0, we get 4L2 delta L2 equals L1 delta L1, or L1 upon L2 equals 1 by 2 under root alpha 1 upon alpha 2. Question 19. A thin uniform rod of mass m and length L is rotating about a frictionless axis passing through one of its ends and perpendicular to the rod. The rod is heated uniformly to increases its temperature by delta theta. Calculate the percentage change in rotational kinetic energy of the rod. Explain why the answer is not 0. Take coefficient of linear expansion of the material of the rod to be alpha. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Moment of inertia of the rod about the rotation axis is I0 equals 1 by 3 mL0 square. When temperature rises, length L changes and hence moment of inertia I change and becomes I equals 1 by 3 mL square. But L equals L0 multiplied by 1 plus alpha delta theta. We get L square equals L0 square multiplied by 1 plus alpha delta theta whole square, which is approximately equals L0 square multiplied by 1 plus 2 alpha delta theta. This implies final moment of inertia I equals I0 multiplied by 1 plus 2 alpha delta theta. Let us consider angular momentum to be capital L. Conservation of angular momentum gives capital L equals capital L0. Rotational kinetic energy Ke before heating K0 equals half I0 omega 0 square equals capital L0 square divided by 2 I0. Rotational kinetic energy Ke after heating K equals half I omega square equals capital L square divided by 2I. Therefore, K upon K0 equals I0 upon I equals 1 by 1 plus 2 alpha delta theta. On solving, we get the percentage change in rotational kinetic energy of the rod equals minus 200 alpha delta theta %. Question 20. A steel tank has internal volume V0 equals 100 liter. It contains half water with volume equals V0 by 2.5 kerosene oil with volume equals V0 by 2 at temperature theta 1 equals 10 degrees Celsius. Calculate the mass of kerosene that flows out of the tank at temperature of theta 2 equals 40 degrees Celsius. Coefficient of cubical expansion for different substances are coefficient of cubical expansion of kerosene oil, gamma K equals 10 to the power of -3 per degree Celsius. Coefficient of cubical expansion of water, gamma W equals 2 into 10 to the power of -4 per degree Celsius. Coefficient of cubical expansion of steel, gamma steel equals 1.2 into 10 to the power of -5 per degree Celsius. Density of kerosene at 10 degrees Celsius is ρ1 equals 0.8 kg per liter. b. In the last problem, the height of water in the container at θ1 equals 10 degrees Celsius as h1 equals 1.0 meters. Find the height of water at θ2 equals 40 degrees Celsius. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Relationship between coefficients of thermal expansions. Change in length delta L due to change in temperature delta T equals original length L into coefficient of linear expansion alpha L into delta T. Change in area delta A due to change in temperature delta T equals original area A into coefficient of area expansion alpha A into delta T. Change in volume delta V due to change in temperature delta T equals original volume V into coefficient of volume expansion alpha V into delta T. Also, alpha A equals 2 alpha L, alpha V equals 3 alpha L, or we can write alpha A by 2 equals alpha V by 3. When steel tank is heated, kerosene oil, water and steel expands by volume delta Vk, delta Vw and delta Vs respectively. Volume of kerosene that spills out, delta V equals delta Vk plus delta Vw minus delta Vs. Or, delta V equals V0 by 2 gamma k delta theta plus V0 by 2 gamma W delta theta minus V0 gamma steel delta theta. Solving it gives volume of kerosene that spills out, delta V equals 1.76 liter. Density of kerosene at θ2, ρ2 equals ρ1 divided by 1 plus gamma k into θ2 minus θ1. Solving which we get density of kerosene at θ2 ρ2 equals 0.78 kg per liter. Therefore, the mass of kerosene oil that flows out, delta M equals delta V multiplied by ρ2. Solving which we get mass of kerosene oil that flows out delta M equals 1.37 kg. Volume of water at θ2 is V equals V0 by 2 into 1 plus gamma W delta theta, where delta theta equals θ2 minus θ1. The area of cross-section of the tank at θ1 is A1 equals volume divided by height equals V0 by 2h1. At θ2 cross-section will be A2 equals A1 into 1 plus beta into delta theta equals A1 into 1 plus 2 by 3 gamma s delta theta. Height of water column, H2 equals V divided by A2. Solving it will give height of water at θ2, H2 equals 1.0057 meters. Question 21. A metal cylinder of radius r is placed on a wooden plank BD. The plank is kept horizontal suspended with the help of two identical string AB and CD each of length L. The temperature coefficient of linear expansion of the cylinder and the strings are α1 and α2 respectively. Angle θ shown in the figure is 30 degrees. It was found that with change in temperature the center of the cylinder did not move. Find the ratio α1 divided by α2, if it is known that L equals 4R. Assume that change in value of theta is negligible for small temperature changes. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Let change in temperature be delta T, due to which length of string increases and hence wooden plank gets displaced downwards. Length of a string changes by delta L equals L alpha 2 delta T. The wooden plank descends by delta Y, which can be seen in the given figure. Delta Y equals delta L upon sine theta. Since theta is given to be 30 degree, sine theta will become 1 by 2. So we get delta Y equals 2 delta L. Change in radius of the ball, delta R equals R alpha 1 delta T. When temperature rises, the wooden plank descends due to increase in length of string. To keep the center of cylinder unmoved static, increase in radius of the ball should be equal to amount by which wooden plank descends. That is, the center of the ball will not move if delta Y equals delta R. It implies 2L alpha 2 delta T equals R alpha 1 delta T. Since it is given L equals 4R. On solving we get alpha 1 divided by alpha 2 equals 8 upon 1. Question 22. A vernier caliper has 10 divisions on vernier scale coinciding with 9 main scale divisions. It is made of a material whose coefficient of linear expansion is alpha equals 10 to the power of -3 per degree Celsius. At 0 degrees Celsius each main scale division equals 1 mm. An object has a length of 10 cm at a temperature of 0 degrees Celsius and its material has coefficient of linear expansion equal to alpha 1 equals 1 into 10 to the power of -4 per degree Celsius. The length of this object is measured using the said vernier caliper when room temperature is 50 degrees Celsius. A. Find the reading on the main scale and the vernier scale. B. The same object is measured at 50 degrees Celsius using a wooden scale whose least count is 1 mm. Write the measured reading using this scale assuming it to be correct at all temperature. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Vernier caliper. A vernier caliper is a measuring device that is used for the measurement of linear dimensions and also for the measurement of diameters of round objects with the help of the measuring jaws to high degrees of precision. It has got one main scale, one vernier scale which is movable. The smallest value up to which an instrument can measure is called least count of that instrument. Least count of vernier caliper equals 1 main scale division minus 1 vernier scale division. At 0 degrees Celsius, 1 main scale division equals 1 mm. Since 10 vernier scale division equals 9 main scale division, we have 1 vernier scale division equals 0.9 main scale division, or 1 vernier scale division equals 0.9 mm. Length of object at 50 degrees Celsius is L equals 100 into 1 plus 10 to the power of minus 4 into 50 mm equals 100.50 millimeters. 1 main scale division at 50 degrees Celsius equals 1 into 1 plus 10 to the power of minus 3 into 50 equals 1.050 millimeters. 1 Vernier scale division at 50 degrees Celsius equals 0.9 into 1 plus 10 to the power of minus 3 into 50 equals 0.945 millimeters. Least count LC equals 1 main scale division minus 1 Vernier scale division equals 0.105 millimeters. Since the length of object at 50 degrees Celsius becomes 100.50 millimeters, we can write L equals 95 times main scale division plus 0.75 millimeters. So, main scale reading equals 95. And Vernier scale reading equals 0.75 divided by 0.105 equals 7. Since the least count of wooden scale is 1 mm, it will not be able to measure 0.50 mm in 100.50 mm. So, wooden scale reading equals 100 plus minus 1 mm. Question 23. A rectangular tank contains water to a height h. A metal rod is hinged to the bottom of the tank so that it can rotate freely in the vertical plane. The length of the rod is L and it remains at rest with a part of it lying above the water surface. In this position the rod makes an angle theta with the vertical. Assume that y equals cos theta. Find fractional change in value of y, when temperature of the system increases by a small value delta T. Coefficient of linear expansion of material of rod and the tank are alpha 1 and alpha 2 respectively. Coefficient of volume expansion of water is gamma. What is necessary condition for theta to increase? We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Torque. A force applied to an object at a point away from the point of rotation will cause a torque. Buoyant force. Buoyant force equals weight of water displaced. Buoyant force equals density of fluid multiplied by gravity g multiplied by volume of submerged object v. But since volume of submerged object v equals mass of submerged object divided by density of object, we can express buoyant force equals mg rho fluid upon rho object. In the given problem, the torque on rod due to gravitational force, F equals mg is mgl by 2 sin theta. The torque on rod due to buoyant force is given by Fbh sec theta by 2 sin theta. Buoyant force Fb equals area of cross-section of rod A multiplied by h sec theta multiplied by density of water ρ multiplied by g. In equilibrium the torque on the rod about the hinge is 0. Therefore, mgl by 2 sin theta equals Fbh sec theta by 2 sin theta. Or, mgl equals ah sec theta whole square rho g. which gives cos theta equals y equals under root a rho upon ml multiplied by volume of water we divided by area of cross-section of tank a 0. By partial differentiation of y we get delta y upon y equals half delta a upon a plus half delta rho upon rho minus half delta L upon L plus delta we upon we minus delta a 0 upon a 0, which gives half 2 alpha 1 delta t plus half minus gamma delta t minus half alpha 1 delta t plus gamma delta t minus 2 alpha 2 delta t, which is equal to 1 by 2 alpha 1 plus gamma minus 4 alpha 2 delta t. If theta increases, y equals cos theta will decrease. This is possible if delta y less than 0 implies 4 alpha 2 greater than alpha 1 plus gamma. Question 24. In the given figure, Graph B shows the variation of potential energy versus atomic separation R in a material. Argue qualitatively to show that if the potential energy graph was a symmetrical one as depicted in Graph A, there would have been no thermal expansion on heating. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. With rise in temperature, the energy rises and atoms oscillate with higher amplitude. If energy is E1 at a temperature T1, the interatomic separation oscillates between x1 to x2 and the mean separation is R1. If temperature rises to T2, the energy becomes higher at E2. The atomic separation now oscillates between x3 and x4 with atoms spending more time at greater distances due to reduced force as can be seen from the graph. Thus the average separation R2 becomes higher than R1 and the material expands. Question 25. In design of a compensated pendulum, a light metal rod of length L0 equals 1.0 meters is attached to a glass tube filled with mercury. Neglecting the mass of the glass tube as well, calculate the height of mercury column in the glass tube so that center of mass of this system does not rise or fall with temperature. Given coefficient of volume expansion of mercury, gamma Hg equals 1.82 times 10 to the power of -4 per Kelvin. Coefficient of linear expansion of glass, alpha glass equals 9 times 10 to the power of -6 per Kelvin. Coefficient of linear expansion of metal, alpha metal equals 1.2 times 10 to the power of -5 per Kelvin. We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. Let mass of Hg equals m. Length of metal rod, L0 equals 1.0 meters. Area of cross-section of the tube be a 0. Position of center of mass from top end of metal rod, YCM0 equals L0 minus H0 by 2. When temperature increases by delta T, L equals L01 plus alpha metal delta T. A equals A01 plus 2 alpha glass delta T. V equals V0 A01 plus gamma delta T. since V equals A multiplied by H. When temperature increases by delta T. Position of center of mass from top end of metal rod, YCMT equals LT minus HT by 2. Which is equal to L01 plus alpha metal delta T minus half a 0 H01 plus gamma delta T divided by A01 plus 2 alpha G delta T. On solving we get YCMT equals YCM0 plus L0 alpha metal delta T minus H0 by 2 gamma minus 2 alpha G delta T. For center of mass of this system to remain constant, we have YCMT equals YCM0. Finally we get H0 equals 2L0 alpha metal divided by gamma minus 2 alpha G, which gives H0 equals 0.146 meters. Question 26. A uniform metal rod AB of mass m and length L is lying on a rough incline. The inclination of the incline and coefficient of friction between the rod and the incline is theta equals 37 degrees and m equals 1.0 respectively. Tan 37 degrees equals 3/4. A. If temperature increases, the rod expands. However, there is a point P on the rod which does not move. Find the distance of this point from the lower end of the rod. B. If the temperature falls, the rod contracts. Once again there is a point Q which does not move. Find distance of Q from the lower end of the rod. C. Will the repeated expansion and contraction cause the rod to slide down? We at the Vector Academy recommend to pause the video and try it yourself before jumping into the solution. A. Let the required distance be L1. Mass per unit length is m divided by L. The lower part AP of the rod has mass m by L1 and the upper part BP has mass m by L into L-1. When heated, the part AP will be moving down and friction on it F1 will be up the incline. The part BP will move up and friction on it will be down, say F2. For equilibrium of the entire rod, F1 minus F2 equals mg sine theta. Mu m by L, L1 g cos theta minus mu m by L, L minus L1 g cos theta equals mg sine theta. Mu by L, L1 minus L plus L1 equals tan theta. 2L1 equals L plus L by mu tan theta. L1 equals L by 2, 1 plus tan theta by mu equals 0.875 L. B. Let the required distance be L1. Mass per unit length is m divided by L. The lower part AQ of the rod has mass m by L1 and the upper part BQ has mass m by L into L-1. In this case the friction on upper part will be up and that on the lower part will be down. For equilibrium of the entire rod, F2 minus F1 equals mg sine theta. Mu m by L, L minus L1 g cos theta minus mu m by L, L1 g cos theta equals mg sin theta. L2 equals L by 2, 1 minus tan theta by mu equals 0.125 L. C. During expansion, net force is acting in downwards direction, given by F2 plus mg sin theta equals F1. During contraction, net force is acting in downwards direction, given by F1 plus mg sin theta equals F2. Hence, net force in both cases is in downward direction. So, rod will slide down. Thanks for watching. Do like the video, comment and share the video in your circle. For more such videos, do subscribe to our YouTube channel, The Vector Academy.